cosmic storm. Floating on whimsical wavelengths is the norm. Dancing through the stars, chasing spectrums of light. Riding the waves that are just out of sight.
Welcome back to another episode of Whimsical Wavelengths. It's all bottoms up here today on the show. No, this is not an episode about drinks, but volcanology. It's hard for me to stay away from Hawaii, mentally at least. Throughout time, I've spent more than a year on the Big Island of Hawaii and loved every minute of it. It isn't the first obvious answer, the weather, versus many other areas of Canada, but for me, as a volcanologist, it has to be because of the two active volcanoes, Kilauea and Mauna Loa, that are accessible through the national park. For me, that's enough right there. But it is also has mind-blowing microclimates, different ecological zones and with different species. The island laid-back culture, too. It's also on the front line of what happens when a new species is introduced into systems they didn't evolve with. Some areas, you might need to sleep with earplugs on the Big Island of Hawaii because of the koki frogs. We're back, audio-wise anyway, to visit Kilauea Volcano due to a recent paper published that I became aware of on LinkedIn. Where to start the intro? Well, Kilauea has been in a near constant state of unrest my entire life. It is also one of the best studied volcanoes in the world. It is well monitored from the ground through gas geochemistry, seismic stations, permanent GPS stations, tilt meters, and a variety of other direct measurements. All this is augmented with remote sensing data as well from space. It's a highly studied place, and there is so much we don't know. So a bit of context and details to make the conversation with today's guest more intelligible. For all the non-volcanically obsessed individuals listening, normally we volcanologists think about eruption dynamics. We think about changes near the surface and how it affects other magma storage in the system. You can think of it in terms of pressure. Erupting one batch of magma lowers the pressure, potentially causing more material to erupt. You can think of it a bit like a cascade of effects. This is a top-down view. It makes sense to think of it this way for volcanoes with long periods of being dormant. It does not mean that mantle dynamics don't have any effect. It's just what happens there does not directly affect the volcanic behavior at the Earth's surface, as far as we can tell, at least normally. In my opinion, Kilauea is a very special volcano. It is a hotspot volcano sitting over what we conceptualize as a mantle plume. This is where hot mantle rocks carrying heat slowly rise from near the core of the planet towards the lithosphere, the solid part of the Earth that we all live on. As that material, even though it's solid, it can still flow. As it begins to rise, the pressure on it begins to drop, which changes its melting point. Once that material, which is slowly flowing through viscous flow, it's not really a liquid, it's just deforming due to stresses. Once it hits a threshold, it can melt. It's a combination of the heat it's carrying and being brought to a level closer to the Earth's surface, which reduces pressure. Remember water? It has a different boiling point, and freezing points for that matter, at different pressures. Like on top of a mountain, it boils at a lower temperature than at sea level. Magma is no different. Okay, so today's topic is Kilauea's magma system, looking at a simplified model that shows sometimes it's bottoms up. So please welcome someone who started in Italy at the University of Bologna and is now a PhD candidate at Rice University, Gaetano Ferrante.
That's good. Yes.
I got it close enough to correct.
No, it's very close.
Well, thanks for being here. And I guess we always kind of start with a little bit about who you are as a guest and how you ended up in the science field. So how did you end up in STEM as a PhD? Was it a childhood dream or was it like something that came much later?
That's a very good question. Well, first of all, Jeff, thanks for having me. It is my first podcast, so I'm quite excited about this.
Well, and to be fair, I jumped at the opportunity because your paper came in actually in my feed in LinkedIn.
Yeah.
And me being a volcanologist, having worked at Kilauea and Mauna Loa, and I was like, this is cool. I want to talk about this. And so I reached out to you, and here you are. So
Yeah.
this is awesome. Maybe it's just because I wanted to nerd out real hard, but that's part of the reason why I have the podcast. But let's
Yeah.
go back to how you ended up in as a PhD first, though.
That's a very tough question. I don't think it was a childhood dream. I've always been interested in science, but I didn't know necessarily what to do with my career up until the very end of my high school. And to be honest, I was really drawn into STEM because of earth science, even if I took an unusual path because I studied physics first for my undergrad. But in reality, I went to Bologna because there was a master's program there called Physics of the Earth System. So that's actually what I was really interested in. And I decided to study physics for my undergrad, but I already knew at that time that I was gonna pivot to the earth science, let's say. But no, not necessarily a childhood dream. One could say that probably living near volcanoes my whole life has kind of shaped that idea in my subconscious, even if I didn't know. But yeah, I discovered it quite late.
So I guess you just mentioned Italy is full of volcanoes, and I have yet to be there. That is on my bucket list. From Etna to Stromboli to Vesuvius, there's just so many stories, so many dynamic systems. So which one did you grow up near, or was it just more of in the culture of Italy? Because I know Italy is not... I mean, yes, Canada and U.S. is way bigger than Italy, but it's not like there's volcanoes everywhere throughout Italy. And then secondly, it's like, why go from there with all of these volcanoes steeped in history to Kilauea? Like, how did you make that transition and jump?
Yeah, so I actually did live near a volcano because I come from a very small town in the south called San Potito San Nitico, which is an hour away from Naples. And so Vesuvius was the closest one, but also Campi Flegrei, which is probably less towering, but as dangerous, if not more.
Scarier.
Yeah, much scarier. So definitely did live near a volcano. I always wanted to study abroad, and I never really had the chance to, partly because when I really made up my mind and decided I wanted to do that, COVID hit, and so I was actually stuck. So I finished my master's in Italy, and then I was considering doing a PhD in the US. And I started looking at different programs, and my advisors back then helped me a lot. And at some point, I stumbled into what eventually became my current project, and I started learning more about Hawaii. And I had never thought about potentially working on Hawaii, let alone going to Hawaii. So for me, it was a whole new thing, and I was very, very intrigued. And I eventually decided to do that. So during my first year, I had the chance to go there for the first time. I spent a week on the Big Island, and then a month in Honolulu while my advisor was doing a sabbatical there. And it was just a life-changing experience.
Yeah, for sure. Like, I don't know. I can't sing the praises of the Big Island enough. Now, I will say the only thing, and I do mean the only thing that drove me crazy about mainly the Big Island was how much drinking and driving actually occurs. Because people show up to the beach with a case of beer, and then they drive home.
That's a good point. I actually never thought of that. But yeah, it must be a big problem. Yeah.
I don't know if it's a big problem. It's just something I noticed everywhere I went.
Okay.
But I mean, like the laid-back atmosphere, the whole different microclimes, just the people generally are just so laid back and chill. There's some caveats to that, of course, but that's caveats to everywhere in this planet Earth that you can find special people. But let's dig into the paper in Kilauea more specifically instead of reminiscing about my time on the Big Island, how I miss it. So the paper is Bottoms Up, Coupling versus Decoupling within Kilauea's Magmatic System. Before we get into the science part, perhaps we should start with, is Kilauea normal?
I think Kilauea is quite special. Well, it is for sure special to me, but I also mean it from a volcanological perspective. In the simplest sense, we have so much data from Kilauea, and it's erupting all the time, that it's hard not to consider it as a special volcano, because it really improved our understanding of volcanoes in general so much by just erupting all the time and giving us all this data and all these opportunities to actually learn more about the dynamics of magma supply and volcanic eruptions in general. So I think it's very special. There are other volcanoes in the world that might be considered similar to Kilauea, but
we're talking just a handful, right? Like,
That's true.
You could almost count on not quite, but you could almost count on one hand persistently active volcanoes, those that erupt all
That's
the
true.
time.
That's true.
Maybe you need two hands for the whole globe, but it's really a small handful of volcanoes.
It's a small handful, and out of all of those, Kilauea is definitely the one that's most monitored and most studied. So it's definitely a special volcano.
Yeah, this is more of a comment for me, from me to say, you look at media, you look at everywhere, like everyone compares whatever they're seeing to Kilauea. Like Kilauea is like the stand-in volcano that everything's compared to. Yet at the same time, you really can't compare Kilauea to anything other than the other Hawaiian volcanoes is kind of where I'm going, because it is so special. Like,
That's true. Yeah.
how much does it erupt? Like year on, year on, year on, after year, after year, after year is just like from the sea floor to where its current summit is. Like you can't really compare it to anything other than another Hawaiian volcano.
Yeah, that's true. Yeah, I agree.
But yeah, we learned so much from looking at, if we want to get really nerdy and talk about geodesy, so the deformation and gravitation of the Earth, to like just the chemical products, to the gas geochemistry, to earthquakes, and yeah, it is so wired.
Yeah, and even just how volcanoes grow. How do they evolve? Yeah. Looking back at the Hawaiian archipelago, we can sort of look back in time. Or forward, and see how eventually these volcanoes will evolve and look in the future. So it's quite special.
Yeah, that said, listeners, there is a lot we don't know about the past and how these volcanoes grow, mainly because they bury everything, and so we don't get access to the younger versions of themselves. Okay, but we're going to cover a lot of different things about Kilauea and hopefully get into some nitty-gritty details, and hopefully I remember to use words that is not going to confuse everyone else, because it's two volcanologists here having a chat, and there's lots of jargon in the way here, so we'll do our best. But to understand the paper and Kilauea's magmatic system, what are the main parts we should really be thinking about here?
Well, I think one very important thing to keep in mind while we talk about this paper is that one of the reasons why Kilauea is special is that it's not only erupting all the time, but it's also being supplied by magma all the time. So what we think is that magma is almost constantly being replenished from depth, from almost 100 kilometers depth where magma first forms. Beneath Hawaii, to the shallow magma chambers, which are around 2 kilometers depth. So magma is always flowing in this system, and this is very important. And as a consequence of that, we think that there's some sort of pathway that connects the region where magma forms to the shallow magma chambers, and that pathway can stay open for long, long time scales. To allow these magma to flow and to allow the volcano to be persistently active. So I think those are two very special elements of Kilauea and two very important things to remember in order to understand this paper and the questions that this paper tried to answer.
Yeah, I guess this is kind of a little bit of inside baseball, because we understand this pretty well, that magma cools. And so to be able to consistently be able to erupt means, like, over decades and decades and decades and decades, means you have to have some way of getting material in somewhat of a constant way to the Earth's surface. And there's not many volcanoes out there that can do this. And so being able to keep things open is very, very difficult when everything wants to cool. You get viscosity. So viscosity increases as it cools. It doesn't want to flow, and then it clogs up the pipes and everything. That's how most volcanoes work, but Kilauea is a little different. One of the things I wanted to kind of really drill into is the shallow magmatic system a little bit before we go deep, looking a bit from the top. So you said there's, now I'm not meaning to contradict anything you say. It's just I think we want to get a little bit deeper. So the way I understand it, which can also change, like from the last time I was at HVO, things can also change in the mindset of those that are studying it. So feel free to correct me, absolutely. But you can think of the shallow system as the pipe in from the base, so that's from the deep mantle source. And then you have a larger summit magma chamber in the southern part of the caldera. And it tends to be the larger one. You have a shallower one underneath Halima'uma'u, which is a pit crater in the summit, which I don't know if that's still legit anymore because now it's erupting and
it's changing shape.
It's changed shape. It's also collapsed in that amount of time. And then you have the rift zones. And at least at one time, because you could track the deformation down the rift zone towards where Pu'o'o was erupting. So the shallow magmatic system is, I guess, bifurcated in some respects, that you have some kind of connection to the individual rift zones, which the East Rift Zone and the Southwest Rift Zone, and as well as, at least there used to be, 2 summit magma chambers. Does that kind of still sum up
correct.
what we think?
Yeah, that's correct.
And they're super dynamic.
They're super dynamic. There might be even more, and there are definitely more areas of magma accumulation even in the summit itself. The 2 ones, like you said, that are usually most active are the Halima'uma'u Reservoir and the South Caldera. And we still don't fully understand the connection between all these magma chambers and to the rift zone. Also, I think because the connection is not static. The connection changes with time. So maybe during an eruption, the connection will be different than during another eruption. And maybe you can reach pressure threshold where new connections can open up. So yeah, it's all correct, yeah. But as far as this particular paper goes, yes, the 2 main reservoirs that we need are the Halima'uma'u Reservoir and the South Caldera Reservoir.
Right. So one is, the Halima'uma'u one is shallower, but I wanted to get, before we look at the bottom processes, I kind of wanted to look at the top-down processes, because these are the ones that if you are sitting there by the computer watching the data coming in from the USGS, looking for your chance to rush out for the next episodic fountaining eruption, you're going to be paying attention to those shallow subsurface activities and stuff like that. So what are some of the examples that you might see in the data?
Yeah, I mean, shallow processes are what we are naturally driven to look at. For example, in the current eruption, during an eruption itself, magma empties out while erupting at the surface, and then at some point it empties out the reservoir so much that it just cannot erupt anymore. And so now the eruption stops and the magma chambers need to replenish until they can erupt again. Or in 2018, so much magma was emptied from the magma chamber that the caldera collapsed. And the caldera collapse actually drove the whole eruption, which otherwise would have stopped much earlier if that didn't happen. So there are a lot of processes, shallow processes, that can actually drive eruptions. And so not everything is driven from the bottom. But what I wanted to convey through this paper is that sometimes not everything is driven by the top either.
Exactly.
Now, I'm going to maybe diverge a little bit here, but it's interesting. I came to this topic from a very different perspective because in my master's, I worked on top-down processes. I think in my master's paper, there's top-down in the title. So I came.
Oh, so there's a backstory of the title.
Yeah, it's a very different process, though. So in my master's, I was very interested in understanding why volcanoes in continental rifts changed their locations over time. And so eventually what we discovered is that the stress field generated by the deepening of the continental rift basin over time, as it becomes deeper and deeper, changes the stress field in the crust. And when magma ascends to the surface in the form of dikes, of hydraulic fractures, the trajectory that these dikes follow are very sensitive to the stress field. And so their location changes over time according to the stress field generated by these very shallow processes. So this is sort of like the definition of a top-down process. But this is, again, a very different process, and it sort of answers your question of why Kilauea is so special, right? Kilauea is erupting all the time. We're not creating, sometimes we are creating new fractures, but these deep pathways thought to be a very well-established pathway that just feeds magma from tens of kilometers of depth to the surface, and it's very stable.
Okay, so I want to take one short deviation only because I have some background knowledge, because otherwise I would have no idea this exists. And then we'll get to those deep ones, those much more stable, and we'll explore that a little bit. But when we think about the shallow stuff, we're usually thinking about differences in pressure. So usually to do with the volatile. So any longtime listener should know that volcanoes erupt. Yes, you need a certain amount of heat. Yes, you need this, you need that. But fundamentally, without volatiles, it'll never erupt. You'll never get a density lower than the rocks it's pushing up through. So when we're starting to look at a lot of these shallow processes, our understanding is that a lot of it's to do with pressure with the volatiles and the rocks or the chamber itself. How much can that chamber hold before having that either fail or push the magma into another location? And so on Kilauea, we see a lot of these things, and they use terminology like DI or ID or DID events, and that stands for deflation and inflation, the D and the I. So the idea is just before a large eruption at the summit where they have the fountaining, you'll get a quick deflation where the whole ground is actually deforming kind of downwards. It's deflating as the pressure is rising to the Earth's surface to cause that eruption. And as you were saying, you were explaining how that you empty the magma chamber, and that's what that deflation is that magma chamber emptying, and then once it's empty and the eruption has stopped, it starts to refill again, which then inflates. And so you can actually get these over the course of 24 hours, even without an eruption, especially during the Pu'o times. And there's just so many different shallow processes that happen as these pressure pulses that have been created by the gas or the volatiles instead of what's down at depth. Because what we down at depth in general, we don't get to directly see. And so that's where this story really turns, because now we're going to talk about the deep section. So what about the deep part more generally, besides it's stable? Like, how do we even know that something changes down there? It's so far away that it's not like our tilt meters or GPSs. We can't see it directly, can we?
That's true. No, we cannot see it directly. We can use some proxies. One very useful data set that volcanologists in Hawaii use to track changes and what happens at depth is CO2 emission rates. So magmas, when they form at depth, they contain dissolved CO2 and other volatiles. But CO2 is interesting because it has a very low solubility, meaning that it wants to come out of the solution, wants to come out of the magma and form bubbles at very large depths. So for Kilauea, for the composition of the magma that is erupted at Kilauea, we think that at depths of about 35 kilometers, CO2 starts to come out of the magma and form bubbles.
35 kilometers?
That's extremely deep. Yes.
Oh my goodness.
So not all of the CO2 will come out there, but it will start coming out at those depths.
As the solubility decreases as it gets to lower pressures. But 35 kilometers, damn.
Yeah.
Just for context, I think the magma forms around 65 kilometers depth, if I remember correctly, for Hawaii. So you're not even halfway there, and you're starting to lose volatiles. I guess that's also, that must come into the whole processes of deep, right? Like the whole rise rates, do they pick up after about 35 kilometers? Like, does the magma start to accelerate because the density is starting to drop?
Well, not necessarily. That's a very good question, and kind of gets in the details of how we perceive magma flow. But at the speeds at which magma ascends, given our estimates of supply rate, are actually quite high. And so the difference in velocity between the gas and the melt is actually not that great. So the magma is already quite fast. It's
Why
about
would it
1
be
meter per second.
Why would it be quite fast at that? Is it density driven, heat driven?
It's mostly pressure driven.
Okay, so
Yeah, we
right.
can get into detail.
Of course, talk nerdy to us.
So, well, let me finish about CO2 first. So, you know, if CO2 tracks the amount of magma that's coming out from depth, then changes in CO2 at the surface are usually interpreted as changes in the rate at which magma is supplied to the shallow plumbing system. And that's essentially what happened in the early 2000s. Measurements of CO2 prior to that were actually very rare, also because it was not changing a lot. If you plot CO2 emission rates as a function of time, it's almost a flat line, because the magma supply rate was thought to be almost constant. But at some point, there was a big bump in 2003 that lasted up until 2007. And so that was interpreted as a change from depth, as a change in the rate at which magma was supplied from depth. So, like you mentioned, we cannot directly see what's happening there, but we can use proxies to understand if something is changing.
No, I've forgotten what the other part of the whole thing I was getting.
No
Oh,
worries,
speed. That's what I was going to...
Yes. Yeah.
You were going to go into the details.
Yeah, so as I said, one main thing to understand the paper is the fact that magma is constantly flowing. Another thing is to think about is pressure. If there is a well-developed conduit that's feeding magma to the volcano up to tens of kilometers of depth to the surface, which it's implied by the fact that melt is always being produced and it's always being transported, then what is the pressure in that conduit? So as far as I see it, there's two really main end members. One is that the pressure follows the weight of the magma itself. So it's a magmastatic pressure profile.
That's a mouthful.
Yeah, it is. It is.
A
so
magmastatic pressure profile.
That's true. Yeah.
So for someone who doesn't, if you can think of I guess we're going to go back to hydrostatic just because that's something everyone who's listening has probably understood. You go deeper into the pool, you have more pressure on your ears. So
exactly.
In this case, we're just saying the deeper down the tube or system, you have more magma above you creating that pressure, magmastatic pressure. Is that what you're saying?
Exactly. That's true.
Okay.
Yeah. So the pool is made of magma. But so as magma actually flows upwards, the pressure decreases. Decreases because mostly of two reasons. One is that you're reducing the weight of the magma column because you're now up higher. The second one is because you're using some of the pressure that you had to overcome friction, viscous drag. So if the pressure inside the magma was only due to the weight of the magma itself, then it means that the pressure that you lose because of viscosity needs to be negligible. And that will happen, for example, if you have a big pipe. The viscous pressure loss, this is how it's usually called, becomes smaller and smaller as the conduit that your fluid is flowing through becomes larger. So if you had a big pipe, then you can actually sustain a magmastatic pressure with depth. The problem with that is that the density of the magma is lower than the density of the rocks, especially if you go to the mantle where rocks become very, very dense. And so at depths of about 40 kilometers, let's say, which for Kilauea is when we think that magma becomes channelized into one individual pathway, we would expect very, very high pressure differences between the magma and the rocks. So it's hard to think of how this can be possible. Well, one option is that it is actually not possible and this pathway will close up. The pressure will eventually close the pipe up or close it up to a point where the pressure balances the pressure outside. Another possibility is that actually the flow of magma, since the magma is hot, will keep melting the surrounding rocks and the rocks will push inward, and so you reach a balance between the melting of the walls and the closure of the pipe to where the pathway can stay open even if the pressure is very low. But I think there's another problem with that, because at Kilauea we have a lot of deep earthquakes. And a lot of these deep earthquakes are thought to be due to magmatic intrusions. They're not thought to be of tectonic origin. So we think that magma is maybe opening up new pathways or moving up through new pathways and breaking rock. And the breaking of those rocks creates new earthquakes. But in order for the magma to break rock, the pressure in the magma needs to be at least the same as in the surrounding rocks, if not higher. And so even if we can keep a pathway open with a lower pressure than the surrounding rocks, I think it's much more reasonable to think that the pressure inside the pathway is at least the same as in the surrounding rock. And so I will introduce a new term and call this lithostatic. So it's the same as before. We're in a pool, but instead of a pool of water or of magma, it's a pool of rocks, and the pressure will be higher.
Right. I understand everything. I just want to make sure that listeners are following along. You're using the word pressure, but you could term it differently and use force and due to things like buoyancy, right?
That's true, yeah.
Okay. Just to make sure that those are following along, we could be talking about a buoyancy force instead of a pressure, but we obviously, in this sphere of research, we use pressure because it's much easier to deal with than 10 to the 16 or 10 to the 32 newtons of force or whatever the heck it would be. Pressure is just a little easier to deal with.
That's true. And so to connect it with the velocity, the reason why I went through this tangent, which is actually not a tangent,
it's not a tangent at all.
It's really the heart of the conceptual model of this paper. If you have such a high pressure gradient, because now we're assuming that the pressure inside the magma is the same as the surrounding rocks, then you have a high driving pressure, and your flow rate through this conduit will be high. And so the velocity can be very high. And this makes sense because, first of all, we can now maintain an open pathway by simply matching the pressure or the force that the surrounding rocks are exerting on the conduit with the pressure that the magma is exerting on the conduit walls, but in the opposite direction. But then we can also maintain flow. We can keep this flow going, which is what we need at Kilauea, because we know that magma is being constantly replenished.
Yeah, it also makes a lot more conceptual sense than trying to melt the wall rocks, because you need to have something that is steady state.
Exactly.
And melting is not something you do particularly quickly, and so how can you keep that as a steady state? But this isn't always steady state, and that's where this whole paper got born from, was the change to that steady state in 2003. So how would that, if you all of a sudden had some more material coming up through that narrow, because it is a narrow pipe, right?
That's true.
So
yeah.
What changes do you expect? Can you have the pipe collapse due to the increase or decrease in pressure? Like what kind of things should we be looking for changes in the volcanic activity at the Earth's surface?
Well, this is a very good question. So our idea for that is that if you have more material coming through, then the pressure inside the pipe needs to increase. But if this pipe is very narrow, then if the pressure increases, then the dimensions of the pipe will increase as well. And if these changes are not too big, we can assume that to first order, the response of this pipe is elastic. And this is an important part of the model, because that's what eventually will lead to our final conclusion. But let's stay here for a moment. So if more magma comes through, then the pressure increases, and the pathway will essentially deform. It will become more spacious to accommodate that new magma. And all of these three things that we mentioned, so flow rate, pressure, and this increase in the and the size of the conduit will propagate upwards and eventually reach the shallow magmatic system. And so in the data, we see that as an increase in CO2 emission rates, like I mentioned before, and also an inflation of the shallow magma chambers. So there's a lot of GPS stations on top of the summit and along the rift zones of Kilauea that can measure how ground moves. And sometimes these stations go up, sometimes they go down. And in 2003, correspondingly, the GPS stations went up, so the volcano inflated. More magma was supplied to these balloons, to these magma chambers as it was erupted, and so they started to inflate.
Yeah. Yeah, that was a wild time. I was actually there for the tail end of that as a volunteer at the Hawaiian Volcano Observatory, taking those differential GPSs, I think they're called Leica systems, and you have them on these little tripods with little buttons so you can quickly level them.
Yeah.
And so one of these shallow events, DID or a DI event, would start. And I don't know why, but Mike Poland, who's now the scientist-in-chief at Yellowstone Observatory, he was the geodesy person at HVO at the time. He trusted me to be able to gather the gear up and go by myself into the caldera and just start like running through all the benchmarks with these to try to capture these events to try to help with the permanent stations. So that was really interesting, a fun time for sure. And it was really like, I don't know how to describe it, but I always, like, as a young, hopefully to be in grad school at the time, I just kind of, I knew that the volcano had changed over time. So, like, you could go before Pu'o'o and Kilauea wouldn't erupt for a few years, and then it would have these fairly, large for Kilauea eruptions, and you had Mauna Ulu in the 60s, and then Pu'o'o started, and then it was just constantly erupting. So to kind of track back this a little, probably way further than your paper really, can you look through time even though we don't have the CO2 measurements required, but could you go back casting to see how some of these events may or may not have been affected by deeper processes?
Well, that's a very good question. One thing I want to say that's probably not answering your question, but I think it's needed first, is that we forgot to mention one important thing, which is that this change that happened in 2003 happened during a period that was extremely stable. So as you mentioned,
all of Pu'o'o's eruptions were really stable. Like for 30 years, it was pretty stable.
Exactly.
But on the ground, you didn't notice that, though. You can only really see how stable it was when you have the chance to step back and look.
Exactly.
Because when you're on the ground, there's all the shallow activity that's happening.
That's true.
And it's constant. You get earthquake swarms, you're getting inflation, deflation events, you're getting the south where you're having this constant slip along the décollement plane, which I'm adding more terminology. Basically, that Kilauea has a mobile south flank, and you can get occasionally you're going to get intrusions into there. And all of this is happening at the same time as these deeper sources. So on the ground, I guarantee you there was some chatter in the background about increasing CO2 and stuff, but the day-to-day science just kept rolling and nobody really gave it too much of a thought until you could look back. So
yeah, that's true. Yeah, because as you said, the scales matter a lot. If you're sitting there like you were, you would have probably felt a lot of changes. If you zoom out at the lithospheric scale, which nobody can until we actually get the data, you probably would have noticed, actually things were not that crazy as I thought.
Well, it depends on what your scale is, because if you're thinking about like, we're going from the prairies in North America over to Kilauea, and all of a sudden you're like, wow, so this was like a fairly large hill, and now it's a giant hole in the ground. Yeah. What happened to you, Pu'o'o? The drastic changes there over the times that I've been there, like, holy smokes.
Yeah.
It's crazy.
But to answer your question, you can actually backtrack changes in magma supply rate even when you don't have CO2 emission rates. Because at the end of the day, it's a mass balance problem, right? The mass that comes in the shallow reservoirs is equal to the mass that comes out plus the change in the mass in the shallow reservoirs. So if you
Over
have
long
measurements
time
of volumes,
scales.
that's true. That's true.
You
Yeah,
can't
but
do it
that's
over
how
the course
they.
of a year.
Yeah, that's how they would estimate supply rate in the absence of CO2 emission rates. So you
Right.
have to average it over a longer time scale. It cannot be a measurement that you make at the scale of the individual CO2 emission rate measurements.
Right.
But you can have estimates over longer periods of time.
All right. Well, we've had a meandering tale of Kilauea's magmatic system, which I'm so glad you came on the podcast for. I am totally nerding out over all of it. But how does that fit in with like today's activity? We're back to that same steady state that was there before 2003, or are we at a different level?
Well, this is very interesting. There seems to be a steady state right now. The eruption is very interesting because it's clearly periodic. It erupts, the volcano erupts for a few hours, and then it doesn't erupt for a few days, and then it erupts again. So it seems like it's very irregular, but in reality, if you average over a long time period, there seems to be a balance between what's supplied and what is erupted. So there seems to be actually some sort of statistical steady state, meaning
Right.
that over a short time span, things seems to be very, very dynamic and changing quite quickly. But if you average them over a longer time, then they're actually not changing a lot. So if we go a little bit back in time and see how we got here, in 2003, there was this big change. There was more magma being supplied to the volcano, and that drove a series of changes in the shallow magmatic system. There was a big eruption in 2007. Then the volcano started inflating again dramatically up until 2018, where the big eruption in the lower East Rift Zone happened that most people remember. So for me, the main upshot of this paper and what we tried to convey is that there's a very big difference in behavior from processes that occur at the bottom and then propagate to the top, and processes that happen at the top. So if we think of what we were talking about before, the fact that if you have more magma being supplied, then the pressure increases and the size of the conduit increases, okay? So if you increase the pressure and you increase the size at depth, both of these processes have the effect of increasing the rate at which magma ascends through this conduit, because you're increasing the driving force, which is the pressure, and you're increasing the size of this pathway. And so you have a lot more magma coming through. So any change at the bottom will significantly affect the top. On the other hand, at the top, we have sort of a negative feedback. So if we change the pressure at the top, let's say we increase it, we are reducing the pressure, the driving force, because now there's a lower pressure difference to drive the flow. But we are also increasing the size of the conduit again. And so these two processes actually compensate each other, and they do not result in big changes in magma supply rate. So why is this important? For example, in 2018, there was a big eruption. People think that the summit reservoirs decompressed of about 20 megapascals. There's a lot. It's a lot of magma being evacuated, and it's a lot of decrease in pressure. And so everyone was expecting something to happen, a new increase in magma supply, because we have now decreased the pressure at the top, and so we can drive more magma in. But in reality, gravity measurements that have been conducted after the eruption didn't really show any change. And so this conceptual model of pressure changes being associated with changes in the size of the pathway, and that leading to a difference between bottom-up processes and top-down processes, can reconcile the fact that there were no changes observed in the rate at which magma was supplied to the volcano after 2018.
Crazy. I just had a random thought that came to me, and it's probably useless, but this is how I conduct science and also my life, which drives people crazy. I throw darts at a dartboard, and more than half the ideas are bad or wrong. But is there any way that this processes that you're describing about creating this pathway and having it, you said elastically deform to open a little wider, is it any possibility that some of these deformations become more permanent? Like it can't fully go back to the same shape, which if you think about it, if they have to stay steady state and now the whole thing is a little bit bigger, you're potentially increasing the magma flow rate or the magma supply rate to the volcano. Like we've always had this problem of trying to understand why Mauna Loa, Mauna Kea, Kilauea are all so large. Like how did their their magma supply increase to the point where they can actually get that big? So is there a mechanism here that as it continues to open up, it just continues to add more supply?
Yeah, I think there could be. I mean, this is a very interesting question and something that I would like to actually pursue in the future. As we mentioned before, what I considered in this particular case was a purely elastic response. So as the pressure went back to what it was before this change in magma supply rate, then the shape of the conduit also went back. But that was also because the changes occurred in a short time relative to the relaxation time of the rocks. But if this
and relaxation time is just for everyone else is like the ability to come back to the same shape. So if your relaxation time is a lot longer, that means to come back to that same shape takes a lot longer. So like a billiard ball, the reaction time is like instantaneously. Whereas this is obviously going to have some time to flow back, if you want to say it, in a viscosity sense to its original shape. Sorry, I just didn't think anybody was following along, just in case they got lost.
Exactly. And sometimes the response of a material can be different according to how fast the force is applied to that material. If I apply a force very fast to silly putty, it will deform in an elastic way. But if I apply it slowly, then it will flow. And this is also true for earth materials. So the deformation that we're talking about here happened over a few years. And given the possible viscosity range of rocks there at depth, even if they're hot, an elastic response is reasonable. But if those changes happened over a longer time scale, then it would be more reasonable to assume that there's also a viscoelastic component, a viscous component. So viscous component is non-recoverable. Once you deform something, it stays that way. It cannot go back. And so I think the answer to your question
is maybe.
Definitely can, yeah. you can have deformations that will alter the shape of this conduit and therefore supply of magma over long time scales.
Wow. So I guess that's where the future of this will go. I mean, is this you said this is an avenue that you want to investigate a bit further. So is that?
Yeah, I would really like to. Like you said before, the puzzling thing about thinking of any other solution to the problem of how this pathway stays open is that you need to be in a steady state, because over the timescales that we've observed, it seems that the volcano is sort of behaving very stably. So I really want to go a little bit deeper into the problem of coupling the flow of magma with the heat that the magma is moving around and losing by conduction to the surrounding rocks. How is it possible that we are in such a steady state even though there's so many things going on at the same time, including, again, changes in the flow rate, which will drive changes in the rate at which heat is transferred through the system. So I would really like to address that in the future. It's definitely on my bucket list.
Yeah, and if you somehow manage to link that to long-term magma supply rate, changing the shape of that, that's a nature paper or a science paper, my friend.
Yeah, and also...
If you manage it, you got to come back on to talk about it, though, okay?
Oh, 100%. I will, yeah. And another question that I really find interesting is that we've been talking about this change that happened in 2003, right? And we've just been assuming that it's more magma coming into the system, but actually we don't really know why there was more magma coming in the system, right? If for 30 years things had been quite stable, what changed in 2003 that drove those transient modifications to the system? Was there simply more magma being produced because maybe it was hotter? Maybe a new portion of the pathway connected to the main pathway and released a pulse of magma that then sent it towards the surface? Those are really interesting questions for me, but they're still open. And it's harder to constrain because, again, like you mentioned, we cannot really see down there. So there's only so much that we can say.
Yeah, all we have is the chemistry of the rocks that come out.
Yeah.
Okay, well, I guess it's call-out time. Because future work, colleagues, whatever you want. However you want to wrap this together before we hit the infamous last question.
Okay. Well, again, like I mentioned at the opening, this was my first podcast, so I feel I should do a shout out to my parents, who will not be able to
understand
this because they don't speak English. But I'll definitely translate it for them and let them know that I mentioned them on.
This is a good segue here, because actually, if you go to YouTube, because you can send it out on YouTube, and because I have a transcript, you can actually do the closed captioning in a whole bunch of different languages.
Okay, that's
it does it automatically. I have looked at this because my wife speaks Farsi, and so it does translate it to Farsi. So they can understand it. I cannot, because I get automatic transcripts. I don't go hand edit them, so maybe the translation might be missing in a few spots. But nevertheless, you can do that.
This is great because they're very curious about my work. But of course, I write in English. My papers are in English, and it takes some effort to translate everything. And so, this is amazing. So shout out to my parents. I'm happy that you will finally be able to hear me or to understand what I say in Italian. Yeah.
Amazing. Yeah. I guess there's people that listen to this podcast all over the world. And so if you want your friend to follow along, maybe the closed captioning is the way to go. I don't know. I don't think I'll be translating this into other languages, although
that takes a lot of effort.
Yeah, well, AI is getting pretty good.
Yeah, that's true.
But I don't know. A problem for another time, because we've come to the last question. The one I ask every guest, and if a guest comes on twice, they'll have to come up ideally with a new joke. What is your favorite science joke?
So I'll tell you this. This is a joke that I heard in my grad school geodynamics class. It's very short. So someone asks a geophysicist or a geodynamicist, they ask them, "What's up?" And the geodynamicist answers, "Well, perpendicular to the geoid."
Oh my goodness. For those that are not following along, the geoid is a way of mapping the mean sea level. It's the lines of equal potential energy of the gravitational field, which can deviate in different spots. That doesn't have to be parallel to the ground surface. And so what is up? Perpendicular to those lines of equal potential energy.
Yeah. I thought you'd appreciate.
I did.
You've done work on gravity, so
That was awesome. Know your host. Okay, well, thank you so much for coming on. And absolutely, if you get into the weeds on and further down this rabbit hole and produce another paper, reach out. I'd happily have you back on.
Thank you so much. It was great to be there. Thank you, Jeff.
That was a real treat. Hopefully for you as well. It was great to reminisce a little bit about Hawaii and get into some brand new research. Awesome. Just awesome. All right, there will be more news about the end of Season 2 as we move a little further forward. And I'll see you guys in 2 weeks.
In a world so chaotic, so misbehaved, echoes of melodies remind us it's all waves. Colors weave stories painting the sky, swaying to rhythms as the galaxies fly by. Ooh, we're tuned in, feeling the beat of the unknown, Her